Okay, hi everyone. I am making this video to explain the electrochemical forces involved in how neurons function, which is obviously very important. We've talked a lot about why neuron functioning is so important, you know, to responding to stimuli in the environment and things like that. So let's just jump right in. So a little chemistry background. All cells have ions. So that translates to all neurons have ions, right? So ions are charge-carrying atoms. We can have atoms that are negatively charged and some that are positively charged. So if we look here at this picture, this is a neutral atom. We can see the neutrons and the protons in the middle and the electrons surrounding. And a neutral atom has the same number of protons and electrons. 6 protons, 6 electrons. When an atom is negatively charged, also known as a negatively charged ion, there are more electrons than protons. So in the rings, we have 6 electrons, and in this little middle part, we have 5 protons. An atom can also be positively charged, which is a positively charged ion, which is when we have more protons than electrons. In this example, there's 6 protons and 5 electrons. So ions can both be negatively charged and positively charged. And ions have imbalance of charges, which is actually naturally occurring and very useful. For instance, an example is like salt. Salt is made up of 2 ions. One is positive, one is negative, and then when they combine together, they actually make a stable pair and that's salt. So an example of an ion is, let's take the sodium. This is the sodium element you can see here. And sodium can have 11 protons and 11 electrons. However, a sodium ion has 10 electrons and 11 protons. We're not going to explain the why this happens in this video, so just take my word for it. But the sodium atom loses 1 electron and becomes a sodium ion. So therefore, because it loses an electron, it becomes positive. So it has more protons than electrons. So this is ions explained. So why are ions important for talking about neurons? So inside the neuron, there is more negative charge, okay? Meaning that there are more negatively charged ions. So naturally, when the neuron is at rest, not firing, there are more negatively charged ions, which leads the neuron to have a negative resting potential, okay? We'll talk about what that is later. The main positive ions, so we have both positive and negative ions, like we said before, involved in the neuron are potassium ions, sodium ions, and calcium ions. And the negative ones are chloride ions. So we'll talk about these more later. The book definitely talks about potassium and sodium a lot. Just to clarify, negative 65 millivolts, if you took the class with me last semester, or if you took the similar class last semester, you'll know that I said negative 70 millivolts, which is actually still correct. And so the resting potential can be anywhere from, I believe, negative 80 to negative 60. So anywhere in that range is fine. I was taught negative 70, and the book says negative 65, so we'll kind of switch back and forth, and I won't expect you guys to have that memorized because it's a little tricky. So we said that there is a resting potential, okay? So what that means, a resting potential, is that naturally, when the neuron is not firing, it's just chilling out, it naturally has a negative charge inside and a positive charge outside. And we're separating the outside and inside with a membrane, of course. And so if I were to actually put an amplifier in, like an amp, right, and read what's going on in the neuron, I would see that there's actually you can read this, that the neuron is just working at this natural level of negative 65 millivolts. which is just a way in which we measure the voltage of a neuron. Okay. So why does resting potential happen? So resting potential reflects potassium ions naturally flowing into and out of the neuron, and the neuron is inactive. So we say that there are more potassium ions in the neuron than sodium ions. Obviously, there's more negative charges than positive ones, but potassium is the big one here. Sodium ions will come into play when we're talking about the action potential, when the neuron fires, when it responds to the environment. So when it's at rest, the membrane is more permeable to the potassium ions. So potassium ions don't really start the spark. They don't start the firecracker to go off. And why does this happen? So there are three things the book talks about that explain why these electrochemical forces work the way they are. And so the three reasons are because opposite charges always want to go together. So they're attracted to each other. So we will always see them trying to get to each other. And diffusion is a big one. So we're always going to see particles trying to move from areas of high to low concentration, which is a big concept involved in why the resting potential happens the way it does. And then something we'll talk about is that these membranes that we see in the neuron, as well as all other cells throughout the body, are selectively permeable, meaning that they have ion-gated channels or pumps, ion pumps, that only allows certain particles to get into and out of the neuron at specific times. And these are very important for when we talk about the action potential. And so you will see that when the neuron is at resting potential, the sodium ions cannot get through, but the potassium can, telling us that the potassium doesn't really excite the neuron in the same way. And they give this picture. I gave it here just to explain it because you might be like, what the heck, and get really dissuaded from continuing to read this chapter with this picture. So you can see here, they're just explaining the whole purpose of this figure is to explain, what it looks like when the neuron is at equilibrium. Okay, so we see when we're saying at equilibrium, equilibrium is just when there is like a acceptable condition for the cell, okay? And so we see here that actually there's more potassium inside, but there's also a negative charge, right? So the negative charge is driving potassium in, but also there's some potassium outside. So it's avoiding this positive charge on the outside. And so these are just showing, this is like, there's nothing really going on. There's no positive or negative charge here. And this thing is just what gives the electrical current. So like, this is what's causing this timer thing here is what's causing there to be a negative charge on the inside of the cell and a positive charge of the outside. And so we see here that this is actually what it kind of looks like for the cell. So the cell is not just stagnant, meaning that it's not just, like one is going in and out and nothing's really happening. There's a lot going on even when the neuron is at rest. That's what this diagram is trying to explain to us. Okay. And now something very important we're going to talk about is called the sodium-potassium pump. So this is something that is, so what happens is it pumps 3 sodium ions out of the cell for every 2 potassium ions in. So this is what actually helps keep the equilibrium, the resting potential that we saw. But it consumes a lot of energy. We are pumping 3 out to get 2 into the cell. That's kind of a losing situation. And this is why the brain requires so much energy. I touch on this because the textbook mentions it, but I am not going to talk about this in class. Okay, and this is another figure from the book that you might recall. And we can see here that there is a very specific concentration of specific molecules outside the cell and inside the cell. So we can see here that only specific molecules are allowed into the cell at resting potential. And so there's all these different ones here and all these different ones inside the cell. And you can see here the concentration of potassium is very low outside the cell, very high inside, and say sodium, very high outside and very low inside, which is kind of what we've been talking about. So this is another graphic of the same exact thing. When the neuron is at equilibrium, when the neuron is at the resting potential, we have an open potassium channels, and we have closed sodium channels. Okay? And there are, of course, some closed potassium channels as well. But what happens when the neuron is excited or receives, when we say a neuron is excited, we mean that a neuron receives a signal from another neuron. So another neuron sends over a neurotransmitter, and then that causes a reaction inside of the neuron. So excited neurons will send an action potential down the axon. So basically, the excited neuron gets excited. It has a brief change in polarization, which is what we call an action potential. So this is the neuron's way of responding to a signal from another neuron. And so the actual thing that we're seeing, the change in polarization, we call this depolarization, which is a change in potential. And so I marked -70 as the resting potential, different from what the book says. But for the purposes of lecture, so the change goes from -70, which is what we're calling the resting potential, to -65, which is what we're calling the depolarization level. But really, the depolarization level can be any level for the action potential to be initiated, or the threshold. So we need to get to some sort of threshold for an action potential to happen, okay? So what happens when the threshold is reached? So let's imagine that a signal is sent from another neuron to the neuron we're looking at under the microscope. And then we see that this signal that the neuron gets is so strong that it causes the neuron to start to depolarize. It's at threshold. So what happens is, and I'm going to show this in the next picture, there will be pictures. So after depolarization, we first get the voltage-gated sodium channels to open. And then sodium rushes into the cell. So to show you this, so we were just using the potassium channels before. Those were just like la 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 la, potassium in and out. We like it inside. Now the sodium is rushing into the cell. Okay, sodium ions are rushing into the cell. And then because of this, now we have both potassium and sodium in the cell, which you may remember, both have positive charges. So we have Na with the plus sign and K with the plus sign, and they're both in the cell. And that rises the threshold to positive 40 millivolts. So now I'm going to jump a few slides. Oops. We now have this, this thing where we see the level at which the neuron is working is all the way up in the positives, okay? Positive electrical value. And then because of this, the potassium channels are like, wait, we need to put the neuron back to right. Like it needs to go back to the normal. And so potassium channels, voltage-gated potassium channels open, but they are much slower to enter than sodium, because remember, sodium rushed into the cell. And then when potassium enters, so the potassium ends up leaving, right? It's leaving the cell and entering too a little bit. It repolarizes it, meaning that it's bringing, like, all these potassiums are leaving. They're like, it's too positive. We need to get out of here. We need some negativity in our life, less optimism. So then it actually, because of this, it like overshoots. Like so much potassium leaves the cell and just the sodium is left, that actually what happens is it hyperpolarizes, meaning that it's almost too much negative and not enough positive in the cell. And then after that, all the gated channels close. And then we return to the resting state of just these channels that transport potassium back and forth. And so this is what that looks like. So at first we have the resting potential here, which is what we know is the potassium channels are open, and they're just freely letting the potassium flow back and forth, potassium ions flow back and forth, la la la, and the sodium channels are closed. And then when the neuron gets excited by another neuron sending the signal, okay, so another neuron sends a strong signal to the neuron and says, hey, you gotta act right now. It reaches this threshold level. And when it reaches this threshold level, we then see the sodium, that signal triggers threshold. When I say threshold, that signal triggers the neuron to let in more sodium through the voltage gated sodium channels. And then the level, like the sodium just keeps coming in, the sodium's just flooding in, and it gets to this crazy high point that the neuron is like, whoa, okay, too much. Now we have to slow back a little bit. So then what happens is the potassium very slowly begins leaving. Okay, so now we see potassium leaving, these gated potassium channels open, and potassium is leaving the cell to the point that too many of them leave. And then so everything starts to go back to normal. And we see that the gated channels close and the cell can return back to its resting potential, and we're back at step one. This happens like in milliseconds, meaning less than seconds, this process over and over and over again. So it's beautiful because this is what allows us to think and process information about the world around us. And so I hope this clarified some things. Okay, see you in class.